All right, y'all. Last law of the day, Newton's third. It's the one that I think is the prettiest. It's the one that I think shows some of the coolest symmetries in the universe as far as Newton's laws go. This one is kind of a restatement of momentum conservation, but it's through the lens of forces. So yeah, all right. Let's just jump in. I'll show you what I mean, and then I'll give a few examples, hopefully, to illuminate the beauty of Newton's third. Okay. So Newton's third law. What is it? The version we've seen before is that for any two interacting bodies, the change in momentum of one of those bodies is equal to the change in momentum of the other body in the opposite direction. So in a collision, for example, if two masses collide with one another, so these are like initial velocities, say, if two masses collide with one another, any velocity change in one mass must be reflected by a velocity change in the other mass. That's required for conservation of momentum, assuming no net external force, right? The beauty of Newton's third law is that it applies to any system, open or closed. It's a statement between any two interacting bodies, regardless of whether that second body is considered inside your system or not, between any two bodies. Okay. So, what I'll do, same as in the last two laws, I'll show you real quickly in a quick little, like, again, hand-wavy derivation, how we get from this momentum lens, this change in momentum type lens, to this force-based or kinematic lens. This time, we're going to use the definition of change in momentum for a particle. So if I've got some body that is under the influence of an external force, delta P of some body, the change in momentum of the body is given by force times change in time. So there's some force that's acting on the body over some time interval. And over that time interval, the change in momentum is given by the force vector times the change in time. The change in momentum is the force scaled by delta t. So as a reminder, force and change in momentum always point in the same direction. Okay, so now we've got change in momentum as force delta t. Let's go ahead and plug that in here, see what pops out. So force on mass 1, on 1, times the, here we go, force times the change in time of the interaction equals negative force on 2 times the time of interaction. Okay, so one thing to notice is that anytime two bodies interact, say in a collision or in gravitation, or if I push my two fingers together, the time of interaction for those objects is the same. So the delta t is going to be the same no matter what. So like, the way I think about this is, if I shake your hand for 2 seconds, you shake my hand for 2 seconds. You know, there's no way around that interaction. I can't shake your hand for 3 seconds and you shake my hand for 1 second. That doesn't make sense. So anytime I've got two bodies that are interacting, i.e. that have forces between them, they have to have forces between them for the same amount of time. So delta t is the same in both cases. So I'll cancel them. What we're left with is that the force on 1 due to 2, the force on body 1 due to body 2, is the opposite of the force on body 2 due to body 1. Okay, so this indexing is kind of minor. I like to do on and by, so the force on 1 by 2 as a result of the interaction with 2, and then on 2 as a result of interaction with 1 by 1. So let me go ahead and draw a picture for this real quick using two bodies. So say that I've got two bodies, the Earth and the Moon. We're going to make the Moon, ooh, interesting. Okay, we're going to make the Moon pink, the default. All right, so there's the Moon. Now the Earth is exerting a force on the Moon. It's a gravitational force on the Moon. So force on Moon from Earth. And the Moon, because the Moon also has mass, is exerting a force on the Earth. So I'd say force on Earth by the Moon. So these two forces are equal in magnitude and opposite in direction. So whatever force the Earth is exerting on the moon is mirrored in a force that the moon exerts on the Earth. So they're kind of like accelerating toward each other, so to speak. Now, because the mass of the moon is so much smaller than that of the Earth, I think it's like a quarter or an eighth, for the most part, what we see is acceleration from the moon. The moon accelerates around the Earth much more noticeably than the Earth accelerates around the moon. But yeah, that's a result of the mass. The forces are the same. The forces are the same. If you like, you can think about this as a local conservation of momentum. If you like, you can think about it as an axiom. Either. One follows from the other. So the forces are equal to each other. Cool. In words, okay, so in words, what does this say? It says that every reaction has an equal and opposite reaction. Or for every force, there is a twin force acting on the source of that force. So if you want to Google it, if you happen to be a Googler, you like to kind of like dig through the background on this stuff. People sometimes call these two forces Newtonian pairs. Newtonian pairs. That's not like language that I'm interested in quizzing you on or anything like that. Don't worry about that. But if you want to dig in a little deeper on this, people sometimes call these Newtonian pairs or Newtonian pair forces. Okay, so I want to dig in one more time on this notion of equal and opposite. So equal's not so bad, right? Equal just means the same in magnitude. So the same length vectors. Each of them has the same force. The moon experiences the same force that the Earth experiences due to the moon. So these two forces are equivalent in size. Opposite means two things. The first thing that I think is useful to think about opposite is that these two vectors are in opposite directions. So like literally in my little chart over here, you can see that the force that the moon is experiencing due to the interaction with the Earth points in the direct opposite direction as the force experienced by the Earth from the moon. So they literally do point like 180 from one another. The other way that I think is sometimes like a nuance that gets lost is that they are opposite in terms of like who they affect. So if I just think about the moon here, the moon is experiencing a force from the Earth on it, right? This equal and opposite thing tells me immediately that the source of that force, in this case the Earth, also experiences an equally sized force. So that's the sense in which they are like mirrored. It's opposite not only in terms of the direction, but also in terms of who experiences the force. The source of any force also acts as a feeler for a force generated by its target. So like here, if the moon's the target of the Earth's force, well, the Earth can't help but experience a force in the opposite direction of whatever force it exerts on the moon. There's equivalent exchange. Okay, I think that's all I really want to say about the third for now. What I wanted to do for a moment was reflect on the great infamous hockey player question. So on last week's quiz, we had these two hockey players. It actually doesn't matter their masses or velocities or what angle they come toward each other. We had these two hockey players, and they were moving toward each other and going to collide. So at the moment of collision, I said, what's a potential force diagram for the scenario? Now, one of the more commonly selected ones, which I'll go ahead and say, I'll put an X up here. This one turns out to be wrong, is that they both experience forces maybe something like this. So equally sized forces, but oriented differently, like not directly against one another. So if I were to break these two to show why maybe this is not a feasible thing, plausible, if I break these two force vectors, these two tentative force vectors, the red tentative force vectors here, into their components, Fx, Fx, and Fy, Fy, I can see that the y components cancel, but the x components don't. The x components stack. So if this were to be a legitimate force diagram, both the top mass, both the top player and the bottom player would experience a net increase in their velocity in the x direction. They would gain momentum in the x direction. And that's a violation of conservation of momentum. That can't happen. So conservation of momentum in the x dimension says that px initial equals px final. The sum px initial equals the sum px final. If they both gain momentum in the x direction, then we can't have the left-hand side be equal to the right-hand side. The right-hand side is going to be greater than the left-hand side. So if they both increase, then the final momentum is going to be larger. I don't have two things canceling to make 0. So here's the right answer. The right answer is any set of forces which are equal and opposite. So this could be an example of a right answer. Force 1, force 2, where force 1 is the same size as force 2. Let's try to make sure that I'm drawing them symmetric. There we go. That's one example of a right answer. The one that I gave as an option, so it could be at any angle as long as they're 180 degrees. Two forces are 180 degrees away from each other. The one that I gave as the right answer was this option. One force pointing up, the other force pointing down, each with equal magnitude. So this is one example of, force. Okay, so I'm going to call this upper person 1, this lower person 2. I'm going to call this force on 2 by 1, and this force on 1 by 2. Notice that when I draw these force diagrams, I'm kind of mixing this is maybe bad practice, but I'm mixing up two independent force diagrams. So this arrow for force is only acting on the upper mass. This arrow for force is acting only on the lower mass. So yeah, okay. So these are not two forces acting at the same point in space. They're acting on two different members of the system. All right, so again, the reason why this is an acceptable answer is because I've got an equal and opposite force in this interaction between these two players. This preserves linear momentum. The very last thing I wanted to say about this is that Newton's laws are unifying. So Newton's third law especially is super sick, super cool, because it unifies many different kinds of force. This is true no matter your length scale. So whether you're two hockey players running into each other, or if you're an electron and a proton, I'll just say plus, and you are interacting with one another, the forces that bind things together, the forces that push things apart, all of them are equal and opposite. All of them come in little pairs like this. An electron that's attracted to a proton experiences a force which is the same in size. So on electron by the proton, on the proton by the electron. They are the same in size and opposite in direction. The difference in the behavior of the two systems comes from the mass. Two subsystems comes from the mass. So the electron here is going to be more accelerated than the proton because the electron is so much lighter than the proton. Okay. Yeah, so again, doesn't matter the type of force, the origin of the force. They come in these pairs, Newtonian pairs.